started. Alright, my style is a little bit slower after all the excitement from just now. No one's going to get married. My girlfriend's going to be at drinks tonight, and please don't get any ideas into her head. Alright, so this is my first time I do Keynote, and I have some slides, but I think I'll spend the majority of the time just showing the cool stuff that we're working on. But just to introduce a little bit, so who am I? Well, this is it. This is my GitHub front page. I work for UC Berkeley for the R OpenSci group, which is where I'm a postdoc. I have a bunch of R packages. These are my commits from the last month. I work on many things concurrently, unfortunately. I have a few packages on CRAN. A little bit about my background. I started using R in my master's degree in 2007, so I'm a little bit younger than some of the older speakers. The first time I used R, I immediately felt that this is not a tool. This is not just a tool for analysts or for scientists. You can build stuff with this. This is free. It connects to everything. You can connect this to websites, to web applications, to data stacks, and that was kind of a novel idea at the time, apparently, because nobody was doing that and nobody was really interested in that. But then there was a professor in my master's degree, Stefan Buren, and he was working on a novel type of clinical diagnosis tool, which is this plot. And the statistics behind it was very complicated, which I didn't find too interesting. But what was really cool is that he had this new diagnostic tool, which allowed clinicians to detect developmental disorders for children by comparing them to certain metrics of the children to a reference population. And he had sort of solved this statistical part of that by taking a large reference sample from clinics in the Netherlands, and then comparing if a certain child, depending on his accomplishments and his characteristics, he was in like the danger zone of being late in development. And when I saw that, it immediately struck me that this is something that you can very quickly serve directly to these clinicians. So his plan was to publish this in a journal and write an R package, and then sort of try to convince hospitals to install R on their machines and maybe train the clinicians to start using R, but of course they don't because they have 100 other things to do. And instead I told him that we should wrap this up into an application, and we did. And it was very cool. It was in my master's degree, and I think the thing is still online. I can show it. And it's super primitive, but this is something that we developed like 10 years ago now. And let's hope it's online. But so the doctor would like enter some metrics here. I'm just filling out some random data now. And the cool thing about it is that this thing would call out to the R server, and it would create this plot that doctors can use and they can interpret, and they could use it right in their hospitals. And that was, back at the time, that was sort of a novel idea, and by now, we have Shiny and everything. But this was sort of what motivated a lot of my work and my research to start using R, taking advantage of it in systems and applications, and not just see it as an end user tool. So what I work on today I work with R OpenSci. So in the meantime, I did my PhD and did a lot of consulting, a lot of other projects. And today I work with the oversight group in UC Berkeley, and we try to develop better tools to improve the data pipeline for researchers. And I get a lot of freedom on what I work. And last year I worked roughly in 4 areas. I developed a bunch of tools, which some of them I will demo. So one area I've worked a lot in is data I/O. So the JSON-like package, which is used by a few people to get data in and out of R, and with JSON becoming sort of the standard data interchange format. That's pretty powerful. And then I sort of build on top of that in the MongoLive package. So the MongoDB is a JSON-oriented database. And so it sort of takes the ID from JSON-like, but then instead of storing it in a string or on disk, you store it in your database, and you get all of these cool features on top of the JSON, standard JSON structure, so that you can query it and stuff. And more recently, I started working on Protolite, which is based on Google's protocol buffers, so it's a binary data interchange format. But I try to sort of take the same concepts, and currently you can serialize R objects to protocol buffers and back. And another area which I will spend the majority of this talk demoing is image processing. So recently we developed more stacks for working with images, and initially this was mostly for graphical images, so for plots. But I've recently learned that actually what many researchers are interested in is medical images and spatial images. And it's sort of funny how the things that we developed mostly to sort of work with graphical images in R, they generalize also to work with satellite data or MRI data or so. And then this year I've worked a lot of stuff in encryption. There's a package OpenSSL which implements every encryption method and all the formats and stuff available today. And then there's some other stuff which I think will become extremely important. But maybe it will take a few more years. But I'm absolutely convinced that data encryption will become a critical part of the data science pipeline, with all the privacy and security concerns that are becoming more critical. And then I spent a lot of time on networking as a code package, which I'll start demoing first. So on to the fun part of the talk. Who here has used the curl package? All right, so that's a few. So I will demo, I'll first show what we currently have, and then I will demo new stuff, which is non-blocking massively concurrent HTTP requests. So in curl, let me switch to Studio. Can you read this? Alright, so traditionally in curl, we have 3 download interfaces. So let me do it this way. So usually you start with a handle. So let me copy the example from the slides actually. So you start with a handle, and then you set some options and some headers, and then there's 3 download interfaces to perform the request. So this is the top block is where I create the handle, which sort of defines the request, but it doesn't actually perform the request yet. And in curl, there's 3 ways to actually execute that request. So the first one I'll demo is curl fetch memory, and this will perform the request, and it will save it will store the results in memory. So that's sort of the fastest and most flexible interface right now. The second interface is curl download, and it will perform the request, and it will write the data immediately to disk. So if you're downloading a file, if you're expecting an enormous amount of data that you don't want to store in memory, you can use this interface, and it will write the results to disk. And the third interface is the curl function, which is uses the R connection API, if you're familiar with that. And this allows for streaming, and it allows for you to incrementally read piecewise data from the stream. So let me demo this. So I have a handle now, H. I hope the Wi-Fi works. So if you do curl fetch memory, you just get an object back, which I call rec here. And that object has sort of all of the response stuff from your HTTP request. So it has the final URL, the status code, the headers, which need the parts, and then some other stuff. And then with the same way, you can do curl download. And then you actually have to write it to a file. And then it has performed exactly the same request, but instead it has stored it from a file. So this is the output. And the third interface we have is the curl connection API. If you're not familiar with that, this is incredibly confusing, but it's the connections in R are sort of a general interface to stream data. So you use the curl function. So you open a connection. It's called curl. Again, you start with the URL. Pass the handle, and then you open the connection, and then you can, for example, you want to read like 2 lines. This only gives you the first 2 lines, and then if I run it again, I get the second 2 lines, and then I get the 5th and the 6th line. If I don't pass any arguments, it reads everything until it's exhausted. So it allows for streaming, right? It allows you to sort of incrementally, if you expect like a huge stream of data and it might not be ready, you sort of can incrementally read the data and process it without having to download everything at first. That's what we currently have. And in this year, we've been working on non-blocking interface. So all of these interfaces are blocking. So while you perform this request, you have to wait for the request to complete. But we're starting to see more and more applications where people do sort of scraping or web crawling. And then it's actually kind of annoying that that's a single request and you have to wait for it to come back and stuff. So instead what we do is like JavaScript, where you just fire up a ton of connections and all concurrently they come in. So the way that works is you first create a new pool. And then you add connections to the pool. So for example, curl fetch multi, and then take an example from the slide. Yeah, so what you have to do is, all right, you define your callback function. So all of this non-blocking is asynchronous. So instead of performing the request and waiting for it to come back and using the return object, you have to define callback functions, and those will be called as the requests come in, right? So as you would do it in JavaScript. So here I have I just create 2 callback functions, and then I add them to the pool. By default, there's a global pool. And then if you run this, everything at once gets run concurrently. And in this case, on purpose, I did two URLs where there's being valid. One gives a 418 error and the other doesn't exist at all. So actually 2 of these requests will fail, just to show that, that the error handler gets triggered. Right, so at first I define these callback functions, and then I schedule these requests, but they don't get executed yet. It returns immediately, and then when I run multi-run, they all get run concurrently, and these callback functions fire as the result comes back. So let me show a bigger example, which shows the power of this. So for example here, just to see how fast this goes. So I'm just going to perform 100 requests. I'm going to create a pool. I'm going to add 100 HTTP requests, and then I'm going to run all of them concurrently. And in this case, just for the example, I'm doing them all to the same URL, to Google. Right, so I create a pool. Oh, and now it's running, and now it's done. Wait, it was going very fast. Let me show it again. So first create the pool, and then the full fetch multi, I add all of these requests. And then I'm just using the same callback functions as before, which just print some error, print some stuff. And then when I do multi-run, they all get run concurrently, and then the result just tells me how many were successful or not. So this is kind of an artificial example, so let me show sort of a more useful example. So there's on GitHub there's an example with the packaging included, which is called crawler.r. It's a little script. You can look it up. It's like 50 lines, but it's really simple, and most of it is just sort of glue stuff. But it only does a few things. It implements a web crawler. So web crawler is what Google does. So it goes from one side to the other. So it's one function which is get links. And basically, it takes an HTML file and it uses HTML2 to extract the hyperlink. So it's used for all anchor text and then extracts the hyperlink, right? And then there's a function called crawl page, which builds on that, which gets the URL, downloads the URL. If it's HTML, it extracts all of these links and returns the links, right? So that that's a node in the web, right? And then there's a crawl function, which has a start page and a timeout, and it just starts with the page, downloads all the links, and then from all these links, it starts visiting those, and then cursor through. So let's see what happens if we run that. Right, so I'm just going to start on a random page here. Right, so depending on the speed of your Wi-Fi, this is going like really fast or just fast. But this is like faster than average HTTP, right? So it's now crawling like randomly the internet. You start at an address, and every time it downloaded all of the links, and then it starts visiting all of those addresses, and then it's getting all of those links and storing everything into an environment. So it's quickly like building a web of all of these pages and what they refer to. And of course, you could like do additional processing stuff. Try to find pages with certain words or so in the process. But I mean, we're on Wi-Fi now, so it's sort of fastest because it's concurrently. But if you're on a really fast network, this can go really fast because all of these things go concurrently. So there's no If you would do this in a blocking way, then if you have one page which is really slow, then everything has to wait for this page to come in, blah, blah, blah. And here, I set the timeout at 1 minute. So we did 2,000 requests in 60 seconds. But yeah, the most important thing is that there's no single point of failure. Does it make sense? Alright, so that was one of the things I wanted to show that I think will become relevant as we start doing more and more with networking in data science and performance is getting more important. Now onto a very different topic, a new package called Magick. Magick is a package for built on the, how much time do I have? That's perfect. Alright, so Magick is a completely new package for image analysis, and it's supposed to fill this gap in R, because sometimes you create a plot, and then the plot itself is nice, but you want to add some stuff, and then you have to go to Photoshop or Paint or so to do that manually, and we kind of want to see if we can fill that gap. So we created a package that does as much as possible of this in R. So it's called Magick, based on Image Magick. You need the development version if you want to install it, because things are going really fast. Install on GitHub, R/Magick. There's a big vignette which should be published soon. So let me just demo it. It's more fun. All right. So you start reloading the package. And if you want to read a package, you just image read, and then you pass the URL or a path on disk. So in this case, I'm going to do Tiger. And the nice thing about it is it takes advantage of RStudio's previewer. So I have an image here, but at the same time it gets previewed here in RStudio. So that creates this, this interactive environment. If you want to, get some metadata about the image, all the functions are prefixed with image underscore, so image info, image, and that gives me like size, the format, and the color space, and all that stuff. If you don't use RStudio, there's some other things. You can use image browse, or in Linux you can use image display. This pops up an X11 window, but that's not that interesting. All right. I really like the Simpsons character, Professor Frink. So I'm going to read from this PNG file on my website, which is called Frink, and I'm going to call it Frink. Right? It's Professor Frink. There we go. Alright, so I'm just going to demo random stuff that you can do with it. Some of the stuff that you might expect. So if you want to add a border, you do something like extend. So this, you have to add the color. There we go. So image border adds a border. There's a lot of parameters that have this special syntax, which is called the geometry. If you want to understand that, you have to look in the vignette, but that kind of defines for all of these. If you want to do cropping or resizing, it defines the size, the area, and the offset. So in this case, I define the border, which is 20 pixels in the x direction and 10 pixels in the y direction. Image trim. It trims of the white space, so your original function was this, but if you want to get rid of the white space, you do this. If you want to crop the image, which is something that you want to do sometimes, So for example, if I just want the head, or is too small? Well, anyway, so I took the image and I cropped the area that is 100 pixels wide, 150 high, and with an offset of 50. So without it, you would get this part, but I wanted to do a little to the right. You can resize it, so image scale. If you want to make it, like small. So if you do times 200, you get it becomes 200 pixels high, and this way it becomes then wide. If you want to rotate it, so you can rotate it so many degrees. Flip and flop. Right, so you can sort of do all of these, these things that you originally would have to revert to Photoshop to. For example, you want to set background, image background, frame. So you can set, you can change the background of the image, and all of this is an image, right? So, at any point you can save this image back to PNG, JPEG, whatever. Right, so this is sort of the standard stuff. Oh wait, this is also this one is fun. So the image fill is flood fill, and most of you are Windows users, so you think of this as the little paint bucket in Paint. So it starts at a certain pixel, and then it's right, so can you see the difference? It was the original. Yeah, this is for the World Cup, right? So, this is like a flood fill. So it starts at a certain point, which is this pixel. So it's 100 times per pixel, of course. So this is like 100 times 200. So it's somewhere here, and then you give the color, and the fuzz factor is it allows you to, the filling to continue even if the colors are not exactly identical, but mostly identical. So this is the geometric distance, the maximal geometric distance between two colors. So if you would lower this, then it would sort of stop at certain points, right? Because there's a little noise. Right? All right. So that was the core stuff. There's a lot of effects which are very cool. So if you want to add a blur, you have to add the size of the blur. So this way you can make it a little more blurry, which is, you have stuff to hide. Noise, adds a little bit of random noise. I'm sure you can see it in the beamer. Charcoal is a sort of cool effect. It gives you makes a charcoal picture. Well, skip over these. If you go into Vignette, there's going to be the effects if you want to just mess around with your images. It's somewhere useful. Something that's actually useful sometimes is you want to annotate images. So for example, you have 1 million images and you want to print some text on top of all of them. So there's image annotate. All right, I just recompiled something. So there's some font conflict between the one I have installed and another one. Thanks, River. Well, let's wait for this. So some of these things, these underlying libraries, they evolve pretty quickly, and then there some conflicts appear. But if you get the current version, that shouldn't appear. All right, so let me show you. Let me continue with showing you how you combine these things. So I'm not sure if it was clear what I just showed, but every time you do an effect, it actually returns a modified copy of the image. So it doesn't, it never modifies the original image, right? So it's R, it's the R philosophy. So if you wanna do multiple things, you have to pipe them together. So I should go to the vignette. Right, so you get stuff like this. So you, for example, here's an example. So we start with reading from a URL, and we want to rotate it, and we want to we add a background, then we add a border, and then we annotate it. So let me show you that that works. Oh shit, it's working again. Anyway, I should skip text examples. Alright, let's get to the most important stuff. So, can you make an animated GIF? Yes, you can.
Yes.
Actually, it's kind of funny, this real story. The reason why I started this package is because my manager really likes animated GIF. And so I was just going to put something together, and then I found this, and I thought, this is interesting, we should do something with it. And now, alright, that's perfect. Alright, so, well, this thing's crunching. Let me explain a little bit to you. So everything I show right now, all of these operations, they work on a single frame, right? So it's an image, and you can rotate it, and flip it, and stuff. But everything in image Magick has been vectorized, right? So everything works the same if you would work with a single image or with a vector of images. And a vector of images, you can interpret it as, for example, layers in an image if you use the Photoshop, or they can be frames in a video, or they can be other things you wanna compose, right? So, for example, if I'm just loading an animated GIF from the internet, because that's, if you search for GIF, that's what you find. So Earth. I just, same way what I just did, image read, and then I gave the URL to a GIF file, right? And then I get the sting, which is the Earth, which everyone has on their website. And if you show the data, you actually see it consists of 44 frames with all the same in the width and height and stuff, right? And everything that you would expect from this object as a regular vector, it works as such, right? So the length of Earth, if you want to get a single frame, you want to just see the first frame, or the second frame, or the first 10 frames, right? So that works. And in R, it's also fun once these indexes work, and sort of everything falls together. So for example, ref is a reverse in R. I didn't implement that. All it does is it sort of reverts frames. So if you do ref Earth, it starts spinning in the other direction. And I didn't implement that. That's just because R sort of it naturally puts everything back together. Right. So these frames, they can be you can see, in this case they are frames in animation, but another application is layers. So often when you compose an image, you think of it as layers. So here I'm just I'm loading 3 images, just JPEG files and PNG files. Alright, so I have 3 images. I have the famous big data image, which is, if you have a big data product, you have to put this image on your website. But still, Professor Fink, and we have the R level, right? And I'm just gonna, with C, just a send concatenator, I'm gonna put them together. So now I have an image. By default, it only prints the first image, but so you have these 3 frames, right? And now, if you perform an operation for image scale, it gets vectorized. So now all of these things get scaled, right? So now image, they all get scaled to. They're not exactly the same size because they were different proportions, but they all get scaled to max 400, right? And now, so now I have these 3 images in one, and I can sort of start combining them. So, for example, a mosaic. and then they get flattened on top of each other. Flatten is the same thing. The only difference between flatten and mosaic is whether the end space gets truncated to the first image or to the maximum size, right? There's also, if you think about it, it's very hard, so different ways in which you can combine images. So if there's like a pixel on different layers, you can make like the top one, by default the top one sort of gets precedence, but you can also start mixing them, so you can, there's different operators, and you can, for example, add, or, and then you can sort of see that. This case is not very useful, but you try to sort of combine these images in a way different from just stacking them on each other. So we only have 5 minutes left. Let me speed up a bit. Image append, just put the images right next to each other. So in this case, show it real quick. So now I just put them right next to each other, and then there's a parameter stack, and then they get on top of each other, right? That makes sense. This is amazing. I just can't show this. So you can actually, you can play with this yourself. This is it's amazing. So here what we do is we just rotate the frame a little bit, and then we put them inside the big data tunnel. So. So all these frames, I told you, they can be these vector elements. They can be frames in an animation, or they can be layers in an image. But they can also be pages in a PDF. So if you read a PDF file, just read a PDF file from the internet, then each page becomes a frame, right? So you can do, you can just get the first page, or and then by default it goes back to PDF, but if we convert it to PNG or so, right, it shows that, right? So that's kind of cool. So for example, if you have a ton of PDF files which you want to like create thumbnails or whatever, or you need to, for whatever reason, you need like page 100 for every file. That's something you can very quickly programmatically pull out, and you can sort of start working with it, just like vectors in R. Some more examples how you would render PDF files. You can also do other packages. All right, animation. So I just showed you how you can read a GIF file, but you can also create a GIF file. So we still have this image file, which was these 3 things, right? So image, it was this one, right? And then if you do image animate, so now it becomes let's try this right there. It becomes an animation. And then you, animating is also kind of difficult because sort of the images appear after one each other, but some of them are transparent, so you have to sort of define what is the operator that defines, like the flattening, defines the pixels. So there's different modes in which you can animate, and you can also change the speed, of course. So this example, so it does only 1 frame per second, and it uses the dispose mode, which sort of every frame clears before it prints a new one, instead of sort of printing them on each other, right? Image morph is very cool. So image morph, you take 2 images, and it creates all of the intermediate images that sort of smoothly transition from one to the other, right? So this example, I took both car logos, the old one and the new one. So this is the new logo, this is the old one, and with image morph, I create, in this case, 12 frames. So now I'm going to create 12 frames that sort of slowly transition the first from the other one. Right? And then if I do image animate, you sort of create this transition that smoothly turns one image into the next. In this case, very ugly, but you can actually make it pretty if you try. Alright, the last example. Oh no, wait, I have way more. 5 more minutes? 2. I'll take some extra time. Everyone does that. Alright, so in this was an example. It was very cool on Twitter. So the dancing banana you might know from early times of the internet. That was like one of the first animated GIFs. You had this dancing banana thing. So this is just a worker sample. So this is the dancing banana as I pulled from the internet. It consists of 8 frames. And what I want to do is I want to create an R logo. And on top of that, I want to have the dancing banana, right? So how would you do this? Well, there's no time for it to think about it. But so what you need to do is you take the R logo, and for each frame, you create a combination of this R logo and the frame, and then you flatten it, and then you put them back together, right? Does that make sense? Right, so that's what I do. Well, that's exactly what I do here. So first I scale them so that they line up a little bit, and then for all of these frames in the banana, I take the R logo and I smash them together, and then yeah, it's a very cool homework example. So let me finish up by something I added last week. So in R, there is already a lot of raster stuff to do image analysis or to do plots. So you can actually take these images. So far we've all worked with these images when they're like JPEG or PNG or whatever, or GIF. But actually you can convert them back to R raster objects, and then you can sort of just plot them on your graphics. So you can send them to the graphics device, right? So as raster is a function in R that sort of converts object to the R native raster format. R native raster format is a terrible legacy format, but you know, so we have to work with. So for example, here I create a plot. And raster image is a function R, so it's a base R function, and what it does is it takes an image. So in this case, I just have my Frank image, right? I didn't even manipulate it. It's just a Frank image that I read, and then you print it on a given position within the plot. So in this case, I wanna print it somewhere here-ish. So these are the X and the Y coordinates in the scale of the plot, right? So there we go. I was very excited when I saw this. I thought I'm going to just create a package that does this all at once. Alright, so, and then there's an alternative method, which is the grid package. I already spoiled it, it's too bad. But so the grid package is slightly different, it's a slightly more recent package. So instead of specifying the position in terms of, you know, the scale of your plot, it sort of just prints it on top of it. So that's sort of, you know. There we go. So, so if you, this is sort of useful if you want to overlay some sort of image or bitmap on top of all of your plots, and you want to have just the relative position. So not the position in terms of your the graphic at hand, but just, you know, this grid raster is just a base package, and it has its coordinates, so you can put it like in the corner of every plot, you know, irrespective of what the size of your plot is. And then there's, you know, also the raster package, which is something that people use for you know, satellite data, medical data, but it's actually not super suitable for actually, yeah, just color pixels, visual data. But we implemented it, so if you have your satellite image and you wanna, you know, you wanna overlay Professor Frank on Australia, so now you can. All right, I think I'm out of time. So thank you.
this was at the beginning, but with the curl non-blocking thing. Can you do status checks and things like that? So while this is running in the background, can you check on the status? So when you ran it, it was basically the run multi that's blocked, right?
Yeah.
All the things are running in parallel, but then you run multi is blocked until back.
Yeah.
So anyway, if you can, this is
I don't understand the question. So what's the question?
So I want to start something in the background.
Well, entirely in the background, but ours.
Yeah.
Yeah, I tried that, and you of course, if you have any other package that puts stuff in the background, you can call curl multi and send it with background. But my experience with our threading is that it's not reliable. There was a lot of weird stuff happening. That's what I initially envisioned, like JavaScript, where you do an AJAX request and it just disappears. And whenever the request comes back, the callback fires. But there's no. But yeah, I end up with this design where you actually have a pool that you control, and then the pool itself is blocking unless you run the pool in parallel threaders, so in which case you can continue. But I found it in ours design, this sort of makes more sense to have you still have the main thread wait, but all of these requests have.
All right, let's thank Jeroen again.